Welcome to State of Simulation, the podcast all about multiphysics simulation, where we stay up to date with what's working, what's not, and what needs to change. Each episode features an open conversation with the engineers and technical leaders shaping the future of physical product development. I'm your host, Jukka Knutinen, and in today's episode, we're speaking with Dr. Sina Sadeghpour, founder of ZeptoNova. With a background in MEMS and advanced electronics, Sina and his team provide design and prototyping services for next-generation sensors, including piezoelectric ultrasound transducers and flexible biomedical wearables. As a partner of Quantscience, they are also utilizing Quantscience AllSolve for their simulation work. In this episode, we explore the industry shift toward piezoelectric thin films and the mechanics behind designing flexible ceramics for biomedical applications. We cover the inherent discrepancies between ideal computer models and real-world cleanroom manufacturing, how iterative simulation workflows bridge that gap, and the two-way relationship between AI and MEMS. Without further ado, let's get started with the show. What kind of MEMS devices are you guys at ZeptoNova working on?
So ZeptoNova is basically a deep technology company that offers services for all sort of MEMS devices to design from scratch, really from concept level to prototyping. So we do design, we do simulation, and we do low volume prototyping. And we have some partners that basically allow us to bridge the gap between prototyping and mass production. But there is basically, let's say, there are three tracks that we are mainly involved, not only offering to our customers, but also internal development and research. And these are in the category of medical devices and healthcare, consumer markets, and cooling solutions, like direct chip cooling solutions. And basically, there are two technology here, main technology involved that we use individually or even in combination. And they are, one is microfluidic technologies, and the other is piezoelectric. So yeah, basically, piezoelectric is the technology that ZeptoNova has deep expertise from past and even today's, and we believe that this is basically a trend in MEMS. So many other technologies and platforms such as electrostatic MEMS or basically magnetic MEMS, etc., are going to be replaced by piezoelectric for many different reasons, like ease of fabrication, reliability, and even better performance. So that's why we also like to continue in this track and bring this technology in different applications, such as optics, medical devices for imaging applications, and recently flexible, basically, devices where we see piezoelectric transducers in devices such as intravascular imaging. So we believe that we see these products hopefully in the market soon, and we already have similar products from different companies and startups in medical sector that uses piezoelectric technology.
So for those outside the microelectronics industry, what exactly do these devices do, and where, in very specific concrete terms, are they used in these end products or end devices?
So basically, the concept of piezoelectric, if I want to focus in that direction, is not new. It's very well known from fundamental physics to already products in the market. If I want to mention, medical sector already have piezoelectric based devices basically in the market that they are using, and they are dominant, but the type of a technology is totally different. Before, they focuses on thick piezoelectric layers where the material manufacturing is followed with a totally different approach. But today we bring the same concept into MEMS by development of thin film piezoelectric. And this becomes a trend today because a few years ago, like a decade ago, we didn't have the technology to produce piezoelectric thin films in the range of few micrometer reliably and basically effectively. But today, thanks to other companies in Japan and Europe and USA that developed machines and basically recipes to develop such materials, we can offer it reliably and bring it into the MEMS technology. So what do they do exactly? Um they do a lot. So conceptually, or let's say fundamentally, they transfer electricity to movements. And that's why they are very attractive for MEMS, because MEMS is a combination of electronics and mechanics. So a piezoelectric material sits really in the middle. And we can make many different sort of devices where we transfer electrical stimulation to mechanical movements. For example, for ultrasound applications, which is the main domain of this type of devices, uh, we make a small, let's say, drum that vibrates and resonates with piezoelectric force and generate ultrasound. And we use this approach to produce ultrasound in the body for the purpose of ultrasonic imaging. So the main advantage, let's say, practically at the end, the result will be the same. So what you gain in terms of the image and everything, but there are a lot behind it. Like economically, they are cheaper. You can produce them in mass. They are much less labor intensive. They are very much miniaturized, and you can combine them with CMOS technology. That's why we are bringing this technology of MEMS devices into applications that the bulk piezoelectric previously is not ideal. For example, for intravascular imaging. Today, intravascular probes, like catheters that you inject into your blood for imaging purposes to diagnose blood clot, they exist based on the classic technology, but each of them cost 1,000 euro, let's say, and they are disposable. So after one time use, you have to dispose it. But imagine that we produce them with MEMS devices by piezoelectric thin films, then the total manufacturing costs and even selling costs will be fraction of what's today, and uh, and that makes a revolution in medical healthcare, because at the moment doctors like to use such a thing for better diagnosis, earlier stage detections, but unfortunately insurance doesn't cover the cost of these catheters. So imagine that we can reduce the cost of one order of magnitude, then they use 10 times more.
So for you guys who are actually working in the design, let's say uh, of this technology, what is it like? What do you have to take into account? How's it like designing and working with this kind of technology?
So one of the things that we always basically engineers, let's say, neglect or uh, take it as trivial in MEMS design is material science, or how to engineer the material. In this specific case, piezoelectric, I can say that the material plays an important role. And plays basically a pillar in the whole design procedure. So therefore, we have to give extra care into material, because even in a small variation in the whole process, like interface of the material, or like basically crystal orientations, crystal quality, temperature, everything can affect the overall reliability, performance, and basically the quality of the material. So therefore, we first do all sort of modeling that is necessary for such a material, and then when we go to the lab, we fix the recipe to not deviate from basically what needs to be achieved. But besides that, modeling, as I said, plays also an important role in the whole design procedure. One of the issues that we have as an engineer is that when we do modeling, the overall result might be not the same as what we practically achieve. And that can be cumbersome, definitely. So we internally believe into some iterative procedure into between modeling, simulation, and practical like fabrication. So we always start with an ideal model because we don't know non-idealities that play role during fabrication. And after the first prototyping, let's say, we feed all our outcomes to the model again, and we do this several iterations that our model then becomes as close as possible to reality. For example, if there are like thermal mismatch, if there are like contamination involved and non-purity involved, then after several iteration, our model basically responds very well. So this is what we follow in ZeptoNova.
So you mentioned there a concept of flexible ceramics, basically. And to someone outside of the field, it can sound even a bit paradoxical. So could you elaborate on what that means? How does it work? Where is it used and all that?
Yeah, definitely. I mean, when we talk about flexible ceramics, it immediately sounds contradictory because to engineers or to people, ceramics are equal to rigidity, are equal to fragility. But when you really try to engineer these type of materials in micro scale, then then they can behave very differently. Uh, Let me give you an example of why flexible ceramics are basically needed in this context. We have several applications that are coming to the market. For example, in medical sector, an ultrasound imaging patch that the patient wear continuously, like for cardio monitoring or other type of applications. And it needs to be stretchable and flexible a bit to form the surface of the body. Or for intravascular imaging, at the tip of the catheter, you need to wrap the transducer around the tip of the catheter to form basically a 360 degrees for the total vessel imaging, and many other applications. That's why if you want to bring piezoelectric into this type of applications and sector in the market, then you need to consider making them flexible. There are different approach that we can engineer and basically uh, make them to act as a stretchable and flexible material, like putting them into a composite in combination of polymers, or basically making different type of islands that are connected with each other with the stretchable and flexible polymers with metal layers embedded into the polymers. So uh, yeah, indeed, it sounds like a paradox, but when you dive into the micro scale, you can perform advanced engineering, and suddenly materials behave in a way that people do not expect.
So what kind of special things, special well, things, for the lack of a better word, you have to consider when you are indeed working with such a material?
Uh, what type of special things? You mean in terms of design or in terms of?
Yeah, let's say in terms of designing of a uh, device that employs this kind of a material.
Yeah.
Is there something you have to take into account that normally you wouldn't, or how does it change things?
One of the things that you need to compromise when you're working with flexible materials, or when you are trying to make ceramics flexible, is you need to compromise between performance and mechanical constraints. So when you make a ceramic flexible, you're basically compromising, or you're sacrificing uh, some details. For example, the crystal uh, orientation or the crystal structure is combined with other materials like polymer to make a composite that gives some stretchability and flexibility to the material. And in that regard, you're compromising the performance of the material. So it's at the end, it's all about a balance between what you want to achieve for that specific application, and what you can do in terms of manufacturing. And by considering all these parameters from the beginning when you are designing the device, then you can go into the right direction to achieve the device and basically meet the demand of the application. So application by application is really different. That's why we don't have a standard rule for flexible structures.
So, as the name of the podcast, State of Simulation, could suggest, or let's say that in the spirit of the name, what is the state of simulation in this field right now? So how is simulation used in all of this?
Yeah, I mean, simulation plays a very important role and is critical, I would say. Without a good simulation tool is not possible. Luckily, in terms of mathematics and the approach of simulation, things in the market, or let's say tools that offer simulations in multi-physics, combining piezoelectric with other type of physics, are quite mature, which is very nice about it. Of course, one of the main problem that we have, and Quansient in this case is innovative, is that ultrasound, or let's say piezoelectric simulation in general, are very intensive. So they require a huge amount of like very fine mesh. They require basically a huge amount of data to be processed, and with conventional tools that are like based on your own workstation, you need to invest heavily on the workstation, or it's very time consuming. So therefore, like the innovative approach that Quasient offer in this case is very useful for us in a sense that we bring everything on cloud, and it's very like iterative type of simulation. So we can basically simulate many different things in parallel without uh, being relied in the classic way of like one simulation finish and then start the next one. So yeah, that is basically uh, that's basically what we follow at ZeptoNova in terms of simulation approach.
How about overall looking at simulation in the field? If your computer says that you now have a perfect design, and then a company goes and actually builds it, fabricates it, is it exactly the same, or how accurately can these simulations depict the reality of these devices?
Yeah, as I pointed out, it's most of the time the first time that you do the simulation, it's not going to be what you achieve in the lab. So because in simulation everything is ideal, the interfaces are ideal, there is no residual stress from beginning. Also, you can define it, of course, if you know it in advance, and many other things. The material thickness is ideal, the etching rates or chemical reactions doesn't like interfere with the process in the simulation. But when you go to the lab, things are totally different. So uh, we always follow an iterative approach in simulation, where we feed the first data, or even second iteration, what we achieve from fabrication, we feed it to the simulation and make the simulation more realistic and close to what we achieve. And after maybe several round of iterations, then we have a model that we can rely on, and basically from the first time we will have good result.
So the biggest topic of today and of the past couple of years, so at least, has been, of course, artificial intelligence, AI. So how does AI? Uh, how do you guys use AI today in your work?
I mean, AI is 100% involved in our daily work, from like typical discussions, consulting technically with the tools, with LLMs, to really use AI for design of structures and mathematical analysis. Um, we still feel that AI in CAD design, or let's say simulation of multiphysics, is a bit lacking and stayed behind the competition in the market. but luckily, yeah, we see that it's coming. For example, even Quantient recently introduced this AI tool that you can discuss with the agent and you can build your model on top. So uh, that's really will be revolutionizing the whole field in future, I believe, if such a thing comes. And basically it can accelerate the design procedure of MEMS devices by several order of magnitudes. But from the other aspect, if you look at it, it's not that we only use AI for our own purposes, but ZeptoNova also offer things to the whole AI community. You know that AIs are very dependent to data centers for processing, data communication, etc. But therefore, there are like uh, more GPUs, more XPUs, like transceivers are introduced into the data centers, into racks that generate a huge amount of heat, and 20 to 30% of the total consumed power is like turns into heat just because of cooling of these devices. And that's why ZeptoNova, as I said, has an active track in designing microfluidics or basic cooling solutions for direct cheap cooling, basically purposes. And we believe that this collaboration that we have with this sector of market will be also something very impressive that we will see hopefully soon in the market in the future.
Well, how about looking ahead in for the next 3 to 5 years? How do you foresee AI changing your work through and through at ZeptoNova?
Yeah, that's a great question. Uh, yeah, again, it's a bilateral relationship basically between ZeptoNova and AI and vice versa. What excites me most over the next 3 to 5 years is the convergence between AI and physical sensing, because you know that today AI mostly lives in digital domain, like image processing, like text processing, uh, and etc. But yeah, but AI system still depends heavily on physical data entering the system, and I believe that MEMS and advanced sensors are essentially the nervous of a future intelligence machine. So uh, basically, they feed the data, they capture all the data in the environment in our world and give it to the AI for better training and better models. Uh, yeah, so I believe that in future we will have a better interaction between computing systems and basically physics, and we will see more emerging miniaturized sensors and edge AI and low power distribution intelligence will happen basically.
Well, that was actually my last question. So, like looking at the MEMS field overall, what and looking ahead in that field, what excites you? And you sort of answered it, but is there anything you want to elaborate on that?
Yeah, as I said, MEMS follows a very ups and downs track in the whole industry. Sometimes people forget about MEMS, and sometimes it becomes a hot topic. Even during the period that you forget about MEMS technology, you see that MEMS devices are everywhere, in your mobile phones, in your smart glasses, in your earpods, everywhere. Uh, but what excites me and what I'm very interested about MEMS today is that again we are in an era that MEMS are at top, are again booming. Not only because of sensing and sensors, but because of different reasons that are coming to the market, different new applications that are caused by AI era, and MEMS can contribute heavily into that. And one of the things is again cooling, um, and packaging. Packaging also, like microprocess manufacturing, heavily are involved into packaging, and you know that things are become much more miniaturized. For example, photonic integrated circuits are closer into electronic integrated circuits, and all required advanced packaging technologies combined with cooling solutions, which are heavily dependent into micro manufacturing and MEMS devices, not the classic MEMS that people have in mind, like gyroscope type of MEMS, but the new era of MEMS. And that's what I'm very excited about it. And honestly, I think there are enormous room for improvement, for being innovative, bringing innovation into simulation tools to basically making a smooth path between design and the end application. So I'm very excited to see that also from simulation tools, and yeah, it would be great to use it in our daily life.
Well, thanks so much for joining.
Thank you very much. It was very nice talking with you.
Thank you for listening to this episode of The State of Simulation. To stay updated with the latest episodes, webinars, blogs, white papers, and more, join our community of more than 8,000 engineers and engineer-minded people on our LinkedIn page, Quanscience. Thank you again, and see you in the next one.